Assalamu alaikum. In our initial lectures on AC machines, we started our discussion with a rectangular loop of wire rotating in a uniform magnetic field created by flat poles. We derived an expression for induced torque in this loop. That torque was given by this relation, where B loop is the flux density vector due to current in the this loop of wire, and Bs is flux density vector due to these magnets. Over there we learned that this machine is not a practical machine. Why? Because there is a big air gap and you need very strong magnets for this machine to work. In today's lecture we shall talk about another arrangement that is more similar to real AC machines, and we shall again derive an expression for induced torque. The arrangement that we shall consider in this lecture is given by this diagram. We have a stationary part which is called the stator, and then inside this we have a rotor made up of ferromagnetic material, and there is a uniform air gap between the rotor and the stator. This air gap is highly exaggerated over here. It is generally very small air gap. So we assume a sinusoidal flux distribution along this air gap. That is flux in the air gap is given by Bs. This is due to the stator, some arrangement on the stator. There is a magnetic field which is shown by these flux lines, and that is sinusoidally distributed. It is function of angle alpha. Angle alpha is measured from this horizontal position. So Bs, that is given by the maximum value of this stator magnetic field, and sine of alpha, that is corresponding to alpha equal to 0. This position, there is flux density is 0, and it is maximum corresponding to alpha equal to 90 degree. On this rotor we have placed a rectangular coil as usual. We have this rectangular coil which is placed on the rotor. So this segment AB is indicated by circle over here, and this segment CD is indicated by another circle over here. This back side of this coil is at the back end and is not visible in this diagram. This front end is also not shown. This coil is supplied with some current, and the polarity of current is indicated in this figure. That is, it is into the surface of board in this conductor, out of the surface of board in this conductor. And we want to derive an expression for induced torque in this machine. So we know that force induced, that is given by IL cross B, where B is the flux density vector and L is the length vector. Direction of L is the same as direction of current in that particular conductor. So let's first study force induced in this conductor. Force in conductor AB, that is given by L cross B. L is out of the surface of board and B is directed in this direction. So both vectors are perpendicular to each other. L cross B is simply equal to L into B, and then the magnitude of force is ILB. Furthermore, flux density is not uniform along the surface, along this air gap. It is function of angle. So this B is basically a function of alpha. So it is Bs sine alpha. So IL Bs sine alpha, that is the magnitude of force. What is direction of force? Direction of force can be determined by direction of this cross product. That is direction of L cross B. L is directed out of the surface of board and B is in this direction. So rotate first vector in the direction of second vector, To determine the direction of their resultant, you can also use the right hand rule. So the direction of force is directed in this direction, and therefore torque due to this conductor AB, that is equal to you know that torque is the cross product of R and F. R is this perpendicular, this distance. You can see that whatever is the position of this conductor, this rotor is rotating at every time instant. This force will always be perpendicular to radius. In this diagram, in this particular situation, this is direction of R directed in this way, and this is direction of force. So both are perpendicular. So R cross F is R multiplied by F. Therefore, the force, the torque due to this conductor AB is R I L Bs sine alpha. And what is the direction of this induced torque? This is in counterclockwise direction. So let's now talk about this conductor, and you can verify that the torque due to this conductor, that is equal to 0. Why? Because this L and B are parallel. L and B, this conductor, this conductor C, segment C, BC is lined like this one, connecting these two conductors at the back end. So this is direction of L, which is parallel to the direction of B, and this is true for all situations. That is when this rotor has rotated to this location, this conductor, this length vector would be this direction, which will be parallel to B vector. So for this segment, segment BC, force induced is equal to 0, hence induced torque is also equal to 0. The same is true for this conductor, and next we talk about this conductor CD. By a similar discussion, we can find the torque induced due to this conductor. That also comes out to be equal to RILB due to conductor CD. That is also equal to RILBs sine alpha. And the direction of this induced torque, what is direction of induced force? L is directed into the surface of board, and B is in this direction. So L cross B is in this direction. So this is force CD. Both the torque induced due to this force is also in counterclockwise direction. Both the torques are in the same direction. Therefore, total torque induced in this machine, that is given by 2RILBs sine alpha. So this is induced torque in this machine. We shall rewrite this expression into another more convenient form. What we observe is that the current in this loop is flowing in this direction, here in this direction, and a current carrying conductor has its own magnetic field. The direction of that magnetic field, this magnetic field can be determined by the grip rule. That is, if you point fingers in the direction of current, thumb will indicate the direction of magnetic field. So this magnetic field due to this current is into the surface of board in this diagram, and in this diagram, this direction current is entering over here and then is moving in this way. So direction of magnetic field due to this current in the coil, that is over here. The strength of that magnetic field due to which due to this current there will be a magnetic field, and strength of that magnetic field, that's denoted by HR. R, that is to indicate that this is the magnetic field due to rotor, this coil on the rotor, that is proportional to the magnitude of this current, and proportionality constant, let's write it by C. This current I is equal to HR over C, and we can replace this current into this expression. We have 2R multiplied by L divided by C HR BS sine alpha. Once this machine is designed, all these things are constant. R is constant, L is constant, C is constant. We write all these constants by this K. So in this expression, Bs is the flux density vector due to the stator magnetic field, and HR is magnetic field strength vector which is due to current in this coil. The directions of this flux density vector, that is upward, and direction of HR is perpendicular to the surface of this coil. Let's show these directions in a more magnified diagram. So here we have the rotor, and we have placed these coils at an angle alpha. So one side of the coil is over here, and other side of the coil, and the angle, this angle is alpha. This angle, Bs is directed upwards, and HR, that is perpendicular to the surface of this coil. HR. The angle between Bs and HR, let's denote it by gamma. So what we observe from this diagram is that gamma is equal to 180 degrees minus alpha. How? So if I extend this line, what is this total angle from here to here? That is 180 degrees. And what is this angle from here to here? That angle is also equal to alpha. The angle between this line and this line is alpha. This line is perpendicular to this line, and this line is perpendicular to this line. Therefore, the angle, this angle will also be equal to alpha. So gamma, which is angle between this vector and this vector, that is equal to total angle 180 degrees minus alpha. And we also know that sine of gamma, that is equal to sine of 180 degrees minus alpha, which is also equal to sine of alpha. This you can verify by expanding this trigonometric relation. Therefore, instead of sine alpha in this expression, we can also replace it with sine of gamma. So we have K HR Bs sine of gamma, where gamma is angle between these two vectors, and therefore this is also equal to HR and cross product of Bs. I have written HR cross Bs to keep the direction of induced torque the same. The torque is in counterclockwise direction. This is in counterclockwise direction. I must take HR cross Bs and not Bs cross HR. Why? This will produce the torque in counterclockwise direction. HR cross Bs in counterclockwise direction, where this produces torque in clockwise direction. So this is not correct. Induced torque in this machine is given by this relation. Furthermore, we notice that Br, the flux density vector due to this magnetic field, that is proportional to the strength of the field. That is, Br is B mu into HR. Therefore, we can also replace HR with Br over mu, and then we have K over mu Br cross Bs. This constant K over mu, we can give it another name. For example, small k in Br into Bs. So what we see is that this expression is quite similar to the one which we derived for a simple loop rotating in a uniform magnetic field and placed in free space. So the expression for torque induced in this machine, that is exactly the same. Over here we had denoted the loop magnetic field by this notation B loop, and here we have only used BR again to denote the magnetic field due to this coil. We can also write this expression in other forms, which are sometimes can be alternately used. This one and those ones can also be alternately used. So let's write those expressions. So in this machine there are two flux density vectors, Bs and Br. Net flux density in the machine, that is given by B net, is equal to Br plus Bs. Remember that these are vectors and this sum is vector sum. B net, the net flux density vector in the machine, that is equal to the flux density vector Br and flux density vector Bs. Or this expression can be equivalently written in this form: Br is equal to the net magnetic flux density minus Bs. Just bring Bs to the left hand side, and then this expression for induced torque, that becomes induced torque is equal to K B net minus Bs cross Bs. Bs is parallel to Bs, so cross product of these two vectors, that is 0, and we have K B net cross Bs. So induced torque is given by this relation, where B net, if I graphically show it, so B net I draw to graphically add these two vectors. We have so this is net flux density vector obtained by phasor sum of this vector and this vector, and Bs is over here. The angle between B net and Bs, that angle is denoted by delta. The angle between net flux density vector and the flux density vector due to stator magnetic field, that angle is denoted by delta. Therefore this expression is equal to K B net Bs sine of delta. So these are different expressions for induced torque in this machine. We shall alternately use these expressions whichever is convenient at different situations. So this expression means that induced torque will be such that it will tend to align both these magnetic fields. That is, it will be maximum when the angle between these two flux density vectors is 90 degrees, and it will be 0 when these vectors are parallel. So induced torque will tend to align the two magnetic fields, and that is basically the basic working principle of synchronous motors. In synchronous motors we have a stator with a set of three-phase coils. These coils are placed 120 degrees apart from each other and supplied with three-phase currents, and the rotor has its own magnetic field, north pole and south pole. So this is the flux density vector Br, and this is the stator magnetic field. And you remember that when these coils are supplied with three-phase currents, this will produce a rotating magnetic field. Bs is rotating, and induced torque will be such that it will tend to align both the magnetic fields. and hence this rotor will keep on chasing the stator magnetic field and it will keep on rotating. So with this we have covered the basics of AC machines, and in the next lecture we shall focus our discussion on synchronous generators, and then we shall talk about synchronous motors.